So let's imagine a block here, and it's sitting on two symmetric pedestals. So that means we have a normal force here and a normal force here. So what I'll do is I'll just call this F1 and F2. So if we assume that the mass of this thing, and let's say the center of mass is in the middle, let's say the mass is 15 newtons, and I want to know where these normal forces. If it's symmetric, in other words, if they're both the same distance from the center of mass here, and everything is symmetric here, the same distance from the ends, everything else, then you can imagine just dividing a line here, and the left half is a mirror image of the right half, so you would expect that F1 equals F2. You know that F1 plus F2 equals mg. So if they're equal to each other, then 2F1 equals mg. So F1 is going to be 7.5 newtons. Okay, this is no different than the hanging thing. So let's make this a little more complicated now. We got our object right here. 20 centimeters long, center mass is in the middle. We're going to still say that mg is 15 newtons. Okay, except now I'm going to put a support right here and right here. So this is going to be 7.5, this will be equal to 7 centimeters from this end. This will be 1 centimeter from that end. Okay, and so I want to figure out, what's F1 and what's F2. Now they're not symmetric. So if you draw a line down the middle, what's on the left is not equal to what's on the right, so you have no reason to expect F1 to be equal to F2. Well, we still can know that force up equals force down, so that's still true. But so that's force up equals force down. So now we want to use our other idea, torque clockwise equals torque counterclockwise. Well, torque, what kind of torque? If you imagine the center of mass right here, this force is trying to turn it this way. This force is trying to turn the object that way. Okay, so F1, if we call that distance D1 to the center of mass, F1 D1 is going to be the clockwise torque, and if we call that D2, F2 D2 is the counterclockwise torque. Well, what's D1 and D2? Okay, if this thing is symmetric, the center of mass will be in the middle, so that's 10 centimeters from each end. So that means D1 is going to be 9 centimeters, and D2 is going to be 3 centimeters. Okay. Well, back over here, this mg is 15 newtons, so we can look at that and say, well, F2 equals 15 newtons minus F1. So I plug that in over here. F1 D1 equals 15 newtons D2 minus F1 D2. So F1 D1 plus D2 equals 15 newtons, the mg, times D2. Okay, so F1 is going to be 15 newtons D2 over D1 plus D2. So be 15 newtons, so F1 is going to be 15 newtons times D2, which was 3 centimeters, divided by D1 plus D2, which is going to be 9 centimeters plus 3 centimeters. So F1 comes out to be equal to 3.75 newtons. You know that F2 equals 15 newtons minus F1. So F2 is going to be 11.25 newtons. So the support closest to the center of mass had more of the weight. Now, this is only one way of solving this problem. As I've said before, there's often more than one way of solving the problem. Because what I did was I said clockwise torque equals counterclockwise torque. And I said that this force was trying to make it rotate this way, that force was trying to make it rotate that way. Well, wait a minute. There's another way of looking at this problem. And that is to say, well, what about if I change the axis of rotation and put the axis of rotation right there? Well, now this force is trying to make it go that way, and now the center of mass is making it go that way. So that means that I can rewrite this clockwise, counterclockwise. So clockwise would be the center of mass, that's mg times d1, and the other is going to be F2 times D1 plus D2. Well, that means that we could say that F2 equals the 15 newtons, that's mg, times D1 over D1 plus D2. And notice we saved a whole bunch of algebra doing this, and we got the exact same equation that we had before that tells us that F2 is 11.25 newtons. But we also know that F1 plus F2 is 15 newtons, so that gives us F1 is 3.75 newtons. So this is exactly the same answers we did before. Okay, what was the difference? The difference was that before I put the axis of rotation at the center of mass. The second time, I put the axis of rotation at one of the pivot points. Well, why would I do one of the unknown supports, F1? Why would I do that? Well, torque is RF sine theta. Okay, so RF sine theta. So basically, it's just going to be that component. So the torque is just going to be the lever arm, the R sine theta times the force. Well, wait a minute. If I have two unknowns, then I have to solve two equations with two unknowns. By changing from the center of mass, because I know the center of mass, I know mg, okay? By changing it so that that provides a known torque, I only have one unknown to solve for, and that's the F. So you can solve this problem multiple ways. It's up to you to decide how you do it. I tend to like to do it the second way here because that's the easier way, but I wanted to show you both ways of doing it. Now we have another possibility. What if I have my same object here, but the center of mass is not in the center of the thing? And so now I should find the mass here and then the mass here. I mean, this would be, for example, putting a scale under one spot right here, 1 centimeter from here, putting a scale 7 centimeters over here. And what you find is you got F1 and F2, and you weigh it. So F1 is 6.2 newtons. Okay, so what's F2? Well, F2 is going to be mg minus F1, so that'll be 15 newtons minus 6.2 newtons, so F2 is going to be 8.8 newtons. Okay, in fact, even if you didn't know that, you could figure out F1 plus F2. If I gave you F1 and F2, then that equals mg. So you could actually work and solve for the mass of the object if you wanted to, if I didn't give that to you. So you can actually solve backwards here. But now we have another problem, and the other problem now is that I don't know where the center of mass is. So I want to find the center of mass. And so I look at it and say, well, I can do the same thing. I can say this distance to the center of mass is D1, that's D2 right here. And so this is going to be mg pulling down right here. So mg d1 is going to be equal to F2 times d1 plus d2. So I'm putting my pivot point right here on the left support again. So the the center of mass, the mg, is providing a clockwise torque, whereas this other one provides the counterclockwise torque. So again, this is going to be clockwise equals the counterclockwise. So d1 is going to be F2 d1 plus d2 divided by mg. So that's going to be 8.8 newtons times, what's d1 plus d2? Well, the entire thing is 20 centimeters, right? So if it's 1 centimeter here, and if that is 7 centimeters right there, then d1 plus d2 is going to be 20 centimeters minus 1 centimeter minus 7 centimeters. And so that's going to be 12 centimeters. So 12 centimeters divided by 15 newtons. And so what we find is D1 is 7.04. It's equal to 7.04 centimeters from the left-hand support. So that means the left-hand support is 1 centimeter over. Center of mass is 7.04 centimeters further over. So that means the center of X position, the center of mass, is 8.04 centimeters from the left end of the box. So now you can actually use this kind of strategy to find the position, the center of mass. Well, it relates to automobiles. So you have an automobile, okay, and so you got an automobile, so we got an automobile here, okay, and the engine is in the front of the automobile. And so that means the center of mass is normally not in the center of the vehicle. The center of mass is slightly forward of the center of the vehicle. That means the normal force on the front wheels is bigger than the normal force on the back wheels. That means the front wheels are going to carry more of the load of stopping. So your front brakes are going to wear more than your back brakes. Okay, well, this is even exaggerated for a pickup truck, because now the bed is mostly empty, and so that means the center of mass is even more forward, and so that means the rear has a very low normal force on it. Well, I mean, that's actually a problem in wet roads or icy roads, because remember, the static friction, the maximum static friction, is equal to mu sub s times the normal. So the smaller the normal, the smaller the static friction. And so, sometimes, if you have really wet roads or slippy roads or something, I've known a couple people with small pickups, and they put heavy loads in the back of the truck, and that weighs it down and gives more grip to the rear wheels. Okay. Now, of course, the disadvantage is that also means you're carrying around more mass, which reduces your fuel efficiency. So, but that's just one of the trade-offs here. And so this also relates to race cars, as to how they change the downforce on different parts of the race car, that change the normal forces on the different wheels, and you adjust that to get the frictional forces that you wish on each wheel.